Imagine a battery that is no longer performing as expected. What's actually limiting its performance? Is lithium-ion diffusion too slow? Is the interface degrading? Or is the electrochemical reaction itself becoming sluggish? In real battery systems, we cannot directly see inside a cell during operation. Instead, we probe internal processes indirectly using electrical signals. And this is exactly where electrochemical impedance spectroscopy, or EIS, becomes powerful. I prefer to describe EIS as a frequency microscope for decoding battery health. My name is Wendy from Uppsala University. In this lecture, I will introduce the measurement principles behind EIS, how impedance is defined, and how we interpret electrochemical signals. So, what exactly is electrochemical impedance spectroscopy? In EIS, we apply a small sinusoidal voltage signal to the battery system. Instead of applying a constant input, we gently shake the ions inside the system. The battery then responds with a current signal. One important thing to remember is that EIS is a small signal measurement. Why? Because batteries are inherently nonlinear systems. If you double the voltage, you don't necessarily get double the current. The response is not perfectly proportional. But when the signal is very small, the system only moves within a narrow operating region. And within this small region, we can approximate the behavior as linear. Linear systems are much easier to analyze. Of course, the signal cannot be too small. Otherwise, the response becomes comparable to measurement noise, and the signal is no longer reliable. Now, we can control how fast the signal oscillates. And this is what we call frequency. At high frequency, we probe the fastest processes in the battery. At low frequencies, we begin to see much slower processes. The signal also has an amplitude, which determines how strong the perturbation is. We need to be careful here, not too large, not too small. Typically, we keep it around 5 to 10 millivolts. The current responses have the same frequency as the applied voltage. The battery doesn't change the signal frequency. We usually denote it by omega. But the current is not perfectly aligned with the voltage. It is slightly delayed, and this is what we call the phase shift. We denote it by phi. And this phase shift carries important information about the internal processes of the battery. We will come back to it later. So, at a single frequency, we apply a sinusoidal voltage and measure the current response. This gives us one data point with a certain amplitude, frequency, and phase. We then repeat this across many frequencies. Each frequency gives us one data point. And when we combine all these data points, we obtain a spectrum. This spectrum tells us how the battery responds across different frequencies, or equivalently across different time scales. And this is exactly what EIS is about. Now, the question becomes, how do we describe this response? At each frequency, we have the input, the output. So what we need is a way to compare these two signals, how strong the response is, and how much it is delayed. To do this, for each frequency, we define a quantity called impedance. A common misunderstanding is to think of impedance as simply the voltage to current ratio in time. But in EIS, we work in the frequency domain. This is analogous to Ohm's law in DC systems, where the resistance is defined as voltage divided by current. In EIS, we generalize this idea. Instead of resistance R, we use impedance Z. And impedance is not a single value. It depends on frequency. Each frequency gives us different impedance response. And impedance describes how the system resists and delay the response at certain frequency. Let's focus on single frequency. Instead of describing the response using amplitude and phase in time domain, we can represent it in another way using two components, the real and imaginary parts of impedance. The real part is in phase with the input, for example, resistive behavior, while the imaginary part is out of phase, for example, capacitive or inductive behavior. Mathematically, we write this as D equals Z prime plus G, Z double prime. The G represents a 90-degree phase shift and is defined as an imaginary number, the square root of -1. Since we have two components, we can represent impedance in a 2D space, and this is a complex plane. We can interpret it physically. The horizontal axis represents the real part of the impedance, and the vertical axis represents the negative imaginary part. Each frequency gives one such point. You may notice that we plot the negative imaginary part. This is simply a convention so that typical electrochemical features appear above the axis. Otherwise, the plot would simply be flipped below the horizontal axis. We don't just look at one frequency. We sweep across a wide range of frequencies, and each frequency gives 1 point. As these points appear one by one, they begin to form a structure, and this structure is what we call the Nyquist plot. As we move along this curve, we are not just moving in space, we are moving across different time scales, and different time scales correspond to different physical processes. So this curve is actually a map of the internal dynamics of the battery. To make this more intuitive, we can directly connect the impedance features to physical processes inside the battery. Look at this side by side. In this mid-frequency region, we see semicircles. This corresponds to processes happening at the electrolyte interface. If we look at this anode particle here, lithium ions need to cross the interface and enter the electrode. This is a charge transfer process. At the same time, there is an SEI layer covering the surface. We used simplified representation, RQ element, to capture both charge transfer and interfacial behavior impedance. As we move further to the lower frequencies, the response shifts to slower processes. Now, lithium ions have already entered the particle and start to diffuse inside the solid. And this diffusion process is much slower. It gives us rise to the 45-degree line. In circuit terms, this is often represented by a Warburg element. You may also notice a small feature at the high frequency end of the spectrum. This region is often influenced by external effects. For example, contact resistance, wiring, or the measurement setup can introduce such inductive behavior. And this feature is typically not related to intrinsic electrochemical processes, so we usually do not interpret this part. Now we link each impedance feature to the physical process and represent it using simple circuit elements. These elements are not the physical themselves, they are a convenient way to approximate and interpret the underlying mechanisms. Let's look at how these impedance features evolve in the real electric vehicle driving scenarios. For example, in real EV usage, batteries experience different charging, discharging strategies, and these can lead to totally different aging pathway. Here, we track battery performance over repeated usage, every 100 full equivalent cycles, similar to period maintenance check in the EVs. What we observe first is a gradual capacity fade over time, but capacity alone doesn't tell you why the battery is degrading. And this is where EIS becomes powerful. By measuring the impedance at different stage of the aging, we can directly observe how the internal processes evolve. For example, at the beginning of life, the spectrum often show a single semicircle. As aging processes, we begin to see multiple semicircles. It reflects the combined effects of SEI layer growth and increasing charge transfer impedance. At the same time, the diffusion limitations become more pronounced. The low frequency response deviates from the ideal 45-degree behavior. It may become flatter or bend upward at very low frequencies, depending on different chemistries. Building on this understanding, we can use the EIS to guide smart charging strategy design. By fitting the impedance spectrum with equivalent circuit models, we can extract parameters that reflect different aging mechanisms. We can track how the SEI resistance evolves and how the charge transfer resistance changes under different charging strategies. By collaborating these parameters over time, we can build models to predict battery behavior under different operating conditions. For example, we find the multi-step charging strategy can significantly reduce the charge transfer impedance. And this is a good strategy, we can adopt it. And this is also why we need EIS. It allows us to non-invasively diagnose the underlying processes and translate the information into actionable strategies to minimize aging and extend battery lifetime. In current battery management systems, equivalent circuit models are widely used to fit such EIS data and model battery performance. They are efficient and practical for onboard diagnosis. However, they are simplified representations. The same impedance responses can often be fitted by multiple circuit configurations. For example, we can use one parallel RQ element or several series RQ elements to model the similar battery behavior. This makes it difficult to uniquely relate parameters to physical processes. In extreme conditions, predictions can become unreliable. For example, when a battery at fully charged status or at low charge status, or with high current charging or discharging protocols. The challenge is how can we not lose any information and directly use EIS data to guide battery system control and optimization. One promising direction is to preserve the full information in the impedance spectrum. Instead of fitting simplified model, we can use the raw impedance combined with data-driven, such as AI. For example, by combining a single EIS measurement with a future charging protocol, the model can predict the next cycle capacity performance, even without any historical data. Just one single EIS measurement can already provide highly accurate predictions. This highlights how rich the information contained in the EIS. In the later part, we will explore this direction in more detail. To conclude this first part, we have seen how EIS allows us to plot the internal physical processes. We start from signals in the time domain, move to frequency, and then connect those responses to aging mechanisms and practical insights. In the later part, we will build on this foundation and explore how the underlying mathematical theory can be translated into practical models and tools for battery diagnosis and control.